Let me give you a second interpretation of this statement, looking at a more of a linear algebraic structure, is the following. So move that a little bit. It's a connection to the column vector space of the dimension 2. For example, so this case here we're looking at is m equals 2. It's easier to draw, but you can think about R3 if m equals 3. So this column vector space is something, this xy plane, simply it's xy plane, so I'm going to draw it here. So this is xy plane. Each of the point here has a coordinate x comma y, but we'd like to look at it as a column vector space. So each point we have it here, for example, if I choose C1 and C2, some two numbers arbitrarily given, then not only we're looking at this as a point, you can associate a vector. So here's the vector arrow. This is the point of application, and this is the arrow, and direction and magnitude is specified by putting this arrow like this. So this is column vector space. So it's not just a collection of points, it was a collection of this arrow, and there's this arithmetic and addition and subtraction and scalar multiplication, and those things are naturally defined, and we often write that column vector in this vertical way like this, and there's matrix multiplication and so on. So this is the beginning of the first course of linear algebra. So the connection between these two things to the kernel of L, this is our interest right now, the solutions of all homogeneous, right? The solutions of all homogeneous function. What is the connection? What is this vector correspond to? So this is going to be correspondence is the following. If there's any function f here whose function value at a is given to c1 and its derivative value is c2. You can think about a function here, and existence and uniqueness theorem says there is only one and only one function with these two initial conditions. So that function corresponds to this arrow, this column vector. And if you choose a different value, and let's say it's a GA, for example like this, second function with a different pair of initial condition, S1 the function value and S2 is a derivative value. And there will be different function points here, S1 comma S2, and again we would like to look at this as a column vector in here. And each column vector or each point in here has one-to-one correspondence with a unique function in here, because each function has this value. If you choose any pair of values, there will be a function that matches that conditions there. So these two worlds as a vector space is kind of behaving exactly the same. So we use the word, fancy word in mathematics called isomorphism. So this is equivalent object in the category of a vector space. So I brought this up this way, so to talk about dimension of this kernel being 2, it's a lot easier to see over here, that because it's more natural that, hey, there's actual vectors, and we can see this is the dimension 2 vector, there are 2 vectors, then you can generate everything. And linear independence, especially the linear independence, is easily understood and in this column vectors. So in that way, I think connecting this, having these two pictures in here, I think it's something useful to see and easily believe. Or you can even use that to write down a nice proof of the fact that a dimension of this kernel is 2 actually, using this column vector linear algebra. So I didn't really write down formal proof, but I think it's sufficient ingredient, so anybody who is motivated and will be able to, with this much of ingredient, will be able to write down a complete proof of this fact. So here's another power, or when we looked at this xy plane instead of this more abstract space of functions, is the following. So here's the xy plane again, and I use the standard notation. This is I vector that has 1, 0, and this j vector that is 0, 1. This is called the standard basis. And if you look at this coordinate is 1, 0, and they definitely correspond to the y1 we're talking about here, y1, that has function value, let me write it this way, sorry about this, y1 prime 0 value. That's this is a correspondent 1 comma 0 goes in there. Of course, down there's y2. A is a 0 value, but the derivative is 1. Write it like this. That function in this kernel space corresponds to this one. So easy to say they exist, and then without knowing what they are, we can still talk about theoretically what they create and how much they cover and stuff like that. But in practice, we don't always deal with this y1, y2. Sometimes there's the more natural or convenient ones available. So sometimes you don't have this ij vector in this space in here, but sometimes you have something else. I'm going to sketch it here. So for example, if supposed to have the v1 vector not necessarily parallel to I or j, and suppose we have something else here, longer, and this is the second vector v2. Suppose we have this two function f1 and f2 in this world, in the kernel. We found those two functions in this space, and their function value and derivative correspond to these two vectors, v1 and v2 in xy plane. As long as they are not parallel to each other in the fancy language and linear term, they are linearly independent. Like this, linearly independent in this two-dimensional version is the same as these two vectors are not parallel or completely opposite to each other. That's the equivalent version. As long as that, you can stretch this one and scalar multiple. That's the same as multiplying the scalar multiple there and scalar multiple there. You can see you can reach anywhere doing this simple column vector arithmetic. That means you can reach anywhere with these two functions by considering these two. So not only all the functions inside the kernel L is a linear combination of y1, y2, if we happen to have f1 and f2 that is linearly independent, which is a same linearly independent sense here in the column vector space, we can write down all the solutions and using in this terms. So let me write that down. This is useful and important statement. So here the similar statement I showed earlier, all the functions inside the kernel of L can be written in terms of f1 and f2 we accidentally found or conveniently it's available for us, and is everything here is now can be written in terms of c1 f1, c2 f2, and we don't always need that special y1 and y2 write down the solution. If we have these two things available to us, and as long as they are linearly independent, then we can generate everything in terms of what we have here. So this is the useful and important. Often we write our solution in this way. So here's a key word: linearly independent. Right? You're not going to always find this special y1, y2. Whatever is available, and make sure we're able to establish this linear independence. These two vectors not parallel to each other, and that's not extendable to all three on a higher dimensional. So we can look at linear independence a little bit more, but that kind of gives you an idea where we're heading. So this is a good example of what I was talking about. Now we're looking at the second order differential equation y double prime minus y equals 0. And remember, we talked about this y1 that has function value 1 and derivative 0. And this one has a function value 0 and derivative 1. These are the special function guaranteed to exist by the existence and uniqueness theorem. But this is not the function we're looking for. Anything you go out and find any two functions whose it's available out there and its correspondence to column vector is linearly independent, not parallel to each other. And then we can write down everything in here in terms of that. So you go out and look for an easiest example. So this is inspection, of course. We're not solving this one algebraically or anything. You look for and you grab the functions that you know you tried it. And you spend some time you realize that, hey, there is this function e to the x. Definitely satisfied if you differentiate it 2 times and the function itself exactly the same. So we got one, and we know we have to find one more. That takes some more time and figure it out. Actually, if you play with e to the negative x, if you differentiate 2 times, this negative multiplied to each other becomes positive 1. So we found these two functions. So as long as they're linearly independent, it's going to be these two important functions. So we're going to write f1 e to the x there, and f2 e to the negative x. Think about why they're linearly independent. The idea is that, so how do you go from here, the column vector? The column vector requires a function value at a and its derivative value at a. So that's what this is. So why don't we choose, because we talked about the solutions around x equals a, so why don't we set a equals 0, so it's easy, and you can choose a equals 1, that'll still work. All this thing is local, so we're looking at the space of solution around x equals a, not necessarily negative infinity to positive infinity. So the KAC a equals 0, that will be 1 comma 1. That's the factor right there. And what about this one here? In this one we have a derivative, so e to the a, that's not derivative, that's the function value. If you differentiate it in negative a, it's negative e to the negative a, right? So a is still 0, so that's going to be 1 comma negative 1. So these are linearly independent if these two vectors are linearly independent in xy plane. So here's x and here's y. This is isomorphic. The space of the kernel of this order 2 homogeneous equation behaves exactly like this column vector, and I'm going to sketch that v1. So v1 is 1 comma 1, so that's this vector here, 1 comma 1, and that's 1 comma negative 1, so that's 1 comma negative 1 down there. That's this vector right there. So this I call is column vector v1, this one I call is column vector v2. These are not parallel to each other. They're linear combination of these two vectors will generate it. So these are two linear, this from here is clear, they are linearly independent. From that we can conclude that from here f1, f2 as a set of two functions are linearly independent. Alright, I wrote it here in Slappy way. So what that means, in everything inside the kernel here is written in terms of, in the form of this function. All the solutions is in the form of this function. So there's that's kind of end of this example. But here's an interesting remark I'd like to make. Okay, I copy down the equation, this homogeneous equation there, y double prime minus y equals 0. Everything this function, every function is written in this form, especially that y1 that we talked about. In this case, a equals 0, so y of 0 equals 1, y1 prime of 0 equals 0. So this function existed in here, with this initial condition must be written in terms of this in this form, and the second function we talked about theoretically also like this can be written in this form. So what you have to do is just simply plug in y equals 0, x equals 0, then differentiate and set this 1, 0 and 0, 1. So when you do that calculation, it turns out y1 is e to the x. So here c1 turns out to be 1/2, and c2 turns out to be 1/2 again. So if you plug in y equals 0, x equals 0, sorry about that, x equals 0 there, then it's 1 and 1, so that picks up 1 there. If you differentiate, you can see if you differentiate, here's y1, differentiated will be constant there, e to the x, and derivative of negative x is negative 1, so it picks up this function here. So if you plug in x equals 0 this time, is 1 minus 1, so they cancel, become 0. So let's see y2. How is y2 is going to look like? It turns out it's e to the x minus e to the negative x divided by 2. So if you plug in x equals 0, 1, 1 cancel, becomes 0. If you differentiate, then here's e to the x. Differentiate one more time, it becomes a positive e to the negative x divided by 2. And if you plug in x equals 0 here, that's 1, 1 divided by 2, so that picks up 1. So it's a little linear algebra system of two equations for C1 and C2 as you go through these two conditions, and you can discover that y1, y2 we talked about theoretically, it can be written specifically in terms of the function that we discovered by inspection. These y1 and y2 are called cosine hyperbolic and sine hyperbolic. It's very unlikely that you find these functions first by inspection, so e to the x and e to the negative x are the so-called generators of the kernel.